So I want to talk about surface integrals in this section, and I thought I would start by running through all of the different types of integrals that we've seen so far in calculus, just to lay out some context. So in Calc 1, we look at definite integrals of single variable functions, and we understand them to represent net area between the function and the x-axis over some interval. And then in this class, we looked at double integrals of two variable functions over regions in the xy plane, and these would represent the net volume sort of in between the surface fxy and the xy plane. And in some instances, if you, like for example, if you replace this integrand with the number 1, then it computes the area of that region D in the xy plane. And then we looked at triple integrals of three variable functions, and it's not entirely, it's not a geometric thing that this triple integral is necessarily computing, but there's all kinds of applications to like center of mass and things in chapter 15 that these triple integrals can compute. And again, if you've got the special case that the integrand is just the function 1, then this triple integral will compute the volume of the object R. Then we moved into chapter 16 and we started seeing line integrals. So we started with a line integral of either a 2 or 3 variable function, depending on if the curve is in 2 dimensions or 3 dimensions, with respect to arc length. And as sort of with the triple integrals, it's not entirely apparent what this line integral computes, especially in the 3-dimensional case, but this type of integral supports some computations that involve vector fields later. So for example, one specific case of a line integral with respect to arc length would be the integrand resulting from taking a vector field and dotting it with the unit tangent of the curve C. And so as we know, this produces an integral that measures the circulation of F along C, or in certain interpretations, the work done by the vector field along C. And then we had another case where a line integral appeared, and that was with the second part of Green's theorem. So a specific line integral that actually quantifies the amount of flow of the vector field across the curve C is represented as a line integral. And we did also see, sort of as part of these line integrals of vector fields, that when you take a particular parameterization of the curve C, then this type of line integral breaks down into these type of line integrals of a function with respect to a variable. So these are sort of all of the line integrals that we've seen so far, and they make an appearance in theorems in this chapter, like Green's theorem. Okay, so in this section, we're moving on to like the higher dimensional version of these integrals. Now that we know how to parameterize surfaces, we're going to develop sort of a surface integral that helps support later the type of surface integrals that we can apply to vector fields. Okay, so that's the goal, and I want to remind you how we compute this type of line integral first, because there's a nice analogy with that computation to the computation we want to make with our surface integrals. So like if you want to compute the line integral of a multivariate function over a curve with respect to arc length, remember the arc length differential form is d lowercase s, then if you have a parameterization of C, you sort of plug the parameterization into F and multiply by the magnitude of the derivative of the parameterization. And like in the specific case of wanting to compute arc length of the curve C, you could just take this differential form here and integrate it. So our arc length formula looks like this, and when you parameterize the curve, of course, it looks like this. Okay, so I want to now move into the higher dimension version of this. We have already seen how to compute surface area of a parametric surface, right? The formula for that looks like this. So if you've got your surface parameterized in the variables u and v over the parameter space D, which is a region in the UV plane, then what you do is you compute this form here, UV cross RU cross RV in magnitude. And remember, that was giving us a measurement of the area of a little parallelogram. And when we sort of form the Riemann sum, it looks like a bunch of these little parallelograms added together, and together they form the estimate for the area of the surface, and in the limit we get ourselves a double integral. So this right here, this unit is the differential form d capital S for surface area, sort of in the same way that this form right here is the differential form for arc length that we used in our line integrals. So this right here is going to be fundamental. When you have a surface parameterized by a vector function RUV, this expression right here appears in the integral for surface area, but it's also going to appear at the end of our surface integrals of other integrands. So I want to be clear here, like in the same way that you can take a line integral of the number 1 to get arc length, but you can also compute line integrals of other integrands, in particular integrands that result from analyzing a vector field in a certain way. We could do the same thing with surfaces. So you can integrate the function 1 over the parametric surface with the differential form for surface area and result in a computation of surface area. But what I want to do from that is develop a surface integral that computes, the integral of a multivariate function across that surface with the differential form of surface area. And again, later, this is going to be the general form of an integral that helps us analyze certain aspects of a vector field across a surface. So in the same way that this integral here looks like this integral with an integrand function added, we're going to do the same thing with our surface integral. So originally I have my surface area double integral. If I add in an integrand function, that's going to be called a surface integral of that integrand function over S. And at the beginning, it's not entirely like apparent, or there's no geometric quantity that this thing is computing, but it's going to support the main theorems of this chapter. Okay, so here it is. This is the surface integral of a multivariate function over a surface, assuming I have a parameterization. So let's practice computing such a thing. Okay, so here is the integrand function. I don't know what that is giving. Maybe it has resulted from some expression involving a vector field. Maybe this is some sort of like density function. Who knows what this is? And the surface that I'm integrating over S is described like this. So in order to use this formula here, I obviously need to parameterize this cone. This is the type of thing we were parameterizing in the previous section. So I'm just going to maybe draw like a very quick picture of this and get it parameterized. Okay, I have parameterized the surface and I've computed the magnitude of RU cross RV because I need to put that into my surface integral. The parameter space over which I'm integrating is this rectangle in the UV plane, and now I'm just ready to set up the double integral. So here's the double integral that I forgot to square root of 2. So here's the double integral that I need to compute. Maybe I'll go over to Wolfram Alpha to get that done. All right, maybe not the worst integral in the world to compute. Sine squared, I would just have to apply a double angle or something. But anyway, Wolfram alpha is giving me this as an answer. So we're ready to do another example. In this example, I'm asked to compute the surface integral of a three-variable function over a part of a cylinder together with a top and bottom disk. So let me draw for you what this surface looks like. You've got your cylinder x squared plus y squared equals 9, and you're cutting it off at the xy plane, and the plane z equals 2. And then you're putting a top on it like this, and a bottom, and then of course you have the sides. So it's like a closed surface, like imagine like a can of beans or something like that. You've got a top, a bottom, and the sides. So there's clearly three parts to the surface, and the surface integral is going to break up into three separate surface integrals. So I'm going to call the sides of the can S1, the bottom let's call S2, and the top S3. And just observe that I have like Cartesian formulas for each of those surfaces, right? Like the side of the can is this cylinder, and then think about what S2 and S3 would be formulaically. S2 is the xy plane, that's z equals 0, right? And S3 is the plane z equals 2. So that's going to be important for thinking about how to parameterize those so that I can compute the surface integral. So breaking it up, I know that the surface integral over the entire surface is going to be the surface integral along the side plus the bottom plus the top. So I'll just do those three surface integrals separately, parameterizing each piece appropriately. So to parameterize the cylinder S1, again, this is like in last section, think about how you would do that. Okay, so I parameterized the cylinder in a natural way, and then I computed RU cross RV, and magnitude was 3. So this is going to be part of the differential form for surface area that goes into my surface integral, at least the first part of it. All right, so now I think I'm ready to go ahead and set up this part of the integral. I'm going to take x squared plus y squared plus z squared from the parameterization, and then multiply it by ds, which is this dA. Okay, if I haven't made any mistakes, then I'm getting 124 pi for the value of that surface integral. So this piece is just the part of the surface integral that represents the outer surface of the can, this S1 part. Now I'm ready to move on to, let's say, S2. I got to parameterize S2. S2 is the plane z equals 0, and then set up the appropriate surface integral for that. So if I want to parameterize z equals 0, I think that using, since it's a round portion of that plane z equals 0, it's reasonable to get sine and cosine sort of rotating as I did on the cylinder. What I need to do, though, is just vary the circles, radii, that the x and y variable are sort of parameterizing. So I may not have said that very well, but this is what will work for me. So if I put a cosine u in for x and a sine u in for v, I know that makes x and y sort of parameterize a circle. If I don't put anything here, it would be a circle of radius 1, right? But I would like for, with the other parameter, I'd like to be able to sort of parameterize every single circle that make up this blue disk right here. So that is like a circle of radius 0 all the way out to a circle of radius 3. So if I put the other parameter here, which controls the radius of the circle in x and y, then this right here will allow those circles to expand outward, and I'll just put a restriction of v from 0 to 3, and that will sort of fill out all of the circles in x and y from radius 0 out to radius 3. So this does it, and then of course u should be between 0 and 2 pi to get the full circles. So there you go. So it's worth pausing and thinking about the RU cross RV vector that I've gotten. Remember that R sub U and R sub V, the partial derivatives of the parameterization of the surface, both of those vectors are contained within the surface. R sub U runs parallel to a U line, which is a grid line within the surface, and RV runs parallel to a V line, which is contained within the surface. So when you take RU cross RV, you would expect it to be perpendicular to the XY plane, which we have here. I only have a K component. In this case, it's pointing downwards. So in any case, I've gotten myself my magnitude of RU cross RV, which goes into the differential form for surface area, and I'm ready to set up the integral. X squared plus y squared is v squared, and z is 0, so plus 0 in here, times v dv du. Okay, and again, if I haven't made any mistakes, then this is the portion of the surface integral across the bottom of the surface. So if you look at the bottom surface compared to the top surface, the only difference is z equals 2. So I could actually come back here to the work that I've done for S2 and get an idea about S3 without doing a bunch of work over again. So the only thing that's going to change with S3 is that instead of z equals 0 right here, I'm going to replace that with z equals, was it 2? Yeah, z equals 2, the top surface. Okay, and that actually is not going to affect the partial derivatives here because the partial derivative of 2 with respect to u or v is also 0. So the RU cross RV is going to look exactly the same. And the other thing that's going to change is the integrand here. So when I take x squared plus y squared, I get my v squared, but then I'm going to get plus z squared, which is plus 4. So I can skip over all this and just jump right to S3. The integral should look like this. Okay, and now I can see that this integral here that I have to compute is just like this one, which was 81 pi over 2, but it's got an extra plus 4v over that region. So I'm just going to compute the integral of 4v dv du and get an answer, and I'll add that to 81 pi over 2. Okay, so now to get the value of the entire surface integral, I just add together the 3 pieces that I had split it up into. So the entire surface integral then over S. Okay, and modulo any arithmetic errors that I made along the way, I'm getting an answer of 241 pi.